Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
OVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming.
TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN Safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO.
Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
The Martian atmosphere is 95% carbon dioxide, a few percent nitrogen, a few percent argon, trace amounts of everything else. But there's still a lot of CO2, and so that's probably the most abundant resource on Mars other than dirt. CO2 has oxygen bound in it, and if we can liberate that oxygen from some of that CO2, then we can use it to do something useful. The goal is to pave the way for future human exploration of Mars by demonstrating the ability to generate oxygen. That's where the magic happens, is inside that box.
NASA is set to launch its next rover to the Red Planet in 2020. Stacked inside are 7 science instruments, 6 of which are focused on sample analysis, like this SuperCam and a spectrometer called Pixel that'll measure chemical signatures inside Martian rocks. And this box getting lowered inside the belly of the rover is MOXIE, or the Mars Oxygen In Situ Resource Utilization Experiment. It's got an agenda separate from the others, and that's to make oxygen on Mars for the first time. Well, at least in real life.
In The Martian, there was something that was called the oxygenator.
If the oxygenator breaks, I'm going to suffocate. If the water reclaimer breaks, I'll die of thirst.
So we jokingly refer to MOXIE as the oxygenator. It's unclear in the movie what technology the oxygenator actually using, but it's very likely that it would be something like MOXIE, but scaled up. MOXIE uses a technology called solid oxide electrolysis. It works a lot like a reverse fuel cell, where instead of putting in a fuel and getting electricity out, we can put electricity in and electrolyze and basically get a fuel and an oxidizer out. On the outside of the rover, we have a small box with a filter. The filter is to make sure that we don't draw in any dust from the Martian atmosphere into our system, because the next thing in the path is a scroll compressor. The scroll compressor takes this low pressure Martian gas from the atmosphere and compresses it and brings it up to something closer to Earth's atmospheric pressure, because the next thing that we do is we run it into this thing. We call this our solid oxide electrolysis stack, and it is basically a layer cake of a bunch of metal plates, which are the dark green things, and then these light colored layers are thin ceramic cells that have particular chemical properties where at high temperature they can conduct electricity using oxygen as the charge carrier. We heat this guy up to about 800 degrees Celsius. You have oxygen ions on one side and you apply a voltage, then you can selectively drive the oxygen through the ceramic membrane and separate it out from whatever's on the other side. It goes through a set of sensors, very much like these sitting here on the table in front of me, and we measure what fraction of CO2 is there. We put CO2 in here, oxygen comes out here, and the waste product, which is a mixture of CO and carbon monoxide and unreacted CO2, comes out here. It's gold because we were concerned that MOXIE itself would run hotter than everything else around it, and we wanted to make sure that we didn't impact any of the nearby electronics boxes inside the rover. And so gold has very low emissivity, which means that it doesn't radiate heat effectively. This particular chemistry process is sort of unique to Mars in its applicability, and also the packaging and how we actually build this system to survive launch and get to Mars. No one has ever done anything like this. MOXIE is going to make about 6 grams per hour of oxygen. It's not very much. It's about enough to keep a small dog alive. We will probably run MOXIE roughly once every 2 months. We don't have the resources available on the rover to run MOXIE for long periods of time continuously, because a lot of the rover energy has to be used for other science that they want to do. The goal for us is to sample different environmental conditions on Mars, so day versus night, summer versus winter, dust storm versus not dust storm, to assess how the technology behaves in response to these changing environmental conditions, because that's what's really useful. What might happen in the future really depends on the technology that NASA decides to go with on Mars. If you only have the CO2 in the atmosphere available, then you'd have something like MOXIE scaled up by about a factor of 200. You'd launch it, deliver it to Mars about 2 years before humans set foot there. It would have a bunch of supporting equipment like a power system and a storage system, and it would sit for 2 years and just generate oxygen and collect it, and then it would be ready for use by the humans when they show up 2 years later. It's really exciting for me to be able to build something that's going to land on another planet. I hope it's going to work the way we expect it to, and that paves the way for future human exploration in the not too distant future. Almost all of my experience prior to coming to JPL and since coming to JPL is in developing hardware, and that has served me very well because you learn a lot of the aspects of how things fit together, what happens at the interfaces. The interfaces are always the most crucial part of a system to make sure things play nice with each other. If you want to build hardware that's going to go to Mars or go to space, you have to know how things get built. Build it and make it work, and that'll serve you very well.
The planet Mars has been mysterious for centuries. But over the past few decades, a fleet of orbiting and landed spacecraft has greatly advanced our understanding of it. Based on this knowledge, Mars scientists are now ready to take the next big step, bringing Martian samples back to Earth, where the full power of our terrestrial laboratories could be applied to unlocking the story of the red planet's geology, climate, and especially its potential for life, either in the past or even today. But however you tackle it, returning samples from Mars is definitely a complicated problem. So how could we actually get a sample from Mars? One approach is to use a series of 3 spacecraft working together like a relay team to deliver samples to Earth. NASA's next Mars rover, currently in development and planned for launch in 2020, will acquire a set of carefully selected samples of rocks and surface material and store them in sealed tubes for possible return to Earth. NASA and the European Space Agency are now working together to explore options for a pair of missions that could take the next steps to bring these samples back. In one scenario, after the Mars 2020 rover has placed its collected samples on the Martian surface, a second follow-on mission would land nearby, deploy a small rover to fetch the samples, and bring them back to the lander, where they would be loaded into a container and placed atop a small rocket. The rocket would then lift off, carrying the samples up into Mars orbit. Waiting in orbit would be a third spacecraft, an Earth return orbiter, that would find the samples in space, catch up with them, capture the container, and bring it back to Earth. With Mars samples safely back on Earth, scientists around the world would be able to study them in state-of-the-art laboratories for decades to come. The payoff of a sample return would be a breakthrough in our understanding of the history of Mars and of the potential for life beyond our home planet.